Hello, welcome to this lecture on modeling, analysis and estimation of three-phase unbalanced power network. We have been talking about the transformer modeling, that is we have been talking about the modeling of the three-phase unbalanced, or rather basically I mean three-phase transformer. So far we have talked about uh, the modeling aspect of the YgYg transformer. So now let us now actually continue with that. So let us today extend that and let us consider an YgD transformer. So we are today we start with YgD1 transformer. Please note that when we are talking about YgD, so YgD x should be always an odd number. So x is basically x basically denotes the group. So it would be only 1, 3, 5, 7, 9, 11, and we have already said that this x is equal to 1 means that essentially the phase difference between the phase A voltage of the start side and the phase A voltage of the delta side would be 30 degree. So basically it would be x into 30 degree. So then therefore if x is equal to 1, so then in that case this phase difference would be 30 degree. If x is equal to say 3, so then this phase difference would be 30 into 3, that is equal to 90 degree, and so on and so forth. And when we are talking about this phase difference, we are essentially saying that the delta side phase A voltage would be lagging from the star side phase A voltage by x into 30 degree. So then therefore in this case when we are basically talking about YgD1 transformer, so that means in this case delta side phase A voltage would be lagging the star side phase A voltage by 30 degree. So to do that, again we start with the very basic primitive diagram of a transformer. As we have said, the basic process is again the same. And once we draw this primitive, then we give the dots. So let's say that the dots are here and here, and the dots are here and here, and then we mark the terminals A1, A2, B1, B2, capital C1, capital C2, and we also mark the terminals at this end as small a1, small a2, small b1, small b2, small c1, small c2. So as of now we have not made any connection, we have just taken the primitive transformers, individual three single phase transformers, and we have not made any connection about the windings and at all. So first we realize this YG. So to realize that, what we do is we connect A2, B2 and C2 together and ground them, and from phase, and then from A1 terminal we say that it is phase A, so the current is IA, and then and then from terminal B1 we say that it is phase B, current is IB, and then from terminal C1 we take phase C, current is I capital C. So we have made the connection at the star side. So now once we made the connection at the star side, then we uh, draw the phasor diagram at the star side. So let's say this is phase A, so this is phase B, so this is phase C. So this is phase A, phase B, and phase C. So we also mark the terminals A1, A2, then B1, B2, and then capital C1, capital C2, and then we ground that point just to reflect this connection. So what we have done, that we have drawn the phasor diagram, and where phase A and phase B and phase C, they are 120-degree apart. And then here, because in this connection we have connected A2, B2 and C2 together, and then basically grounded it. So then therefore here also we have indicated the same, that we have actually tied up A2, B2 and C2 together and then grounded it. So now this finishes the phasor diagram at the star side. Now to go at the delta side, so let us first, so these are the virtual A phase, virtual B phase and virtual C phase, right, at the start site corresponding to phase. But then because it is YgD1, so and my phase difference is 30-degree lag, 30-degree lag, so then therefore my phase A voltage would be somewhere here. So my phase A voltage would be somewhere here. So this is 30-degree, and then my phase B voltage would be shifted again from this by 30-degree, and my phase C voltage would be shifted from this by 30-degree. That's how it will look like. Alright. So it is phase A, it is phase B, it is phase C. But because it is delta, please note that these are nothing but the virtual phase A voltage, virtual phase B voltage and virtual phase C voltage. But because this side is connected in delta, so we will not actually get these virtual phase A voltage, virtual phase B voltage, virtual phase C voltage. What we will get is, we will essentially get the line to line voltage. So to get this line to line voltage, what we get is, we actually get between phase A to B, so phase A to B, and then we will get phase between phase B to C, and then we will get between phase C to A, right. So I will make the drawing a little more neat. So this is phase B voltage, this is virtual phase C voltage, and this is phase A, this is phase B, and this is phase C. So these are the actual. So then basically these vectors drawn in green, they are nothing but the actual voltages, line to line voltages, what we will get. So now you have to mark the terminal. Because this one is parallel to this, so then therefore this terminal would be A1, A2, and because this is parallel to this would be B1, B2, and because this one is parallel to this, so it will be C1, C2. Let me again draw it a little more clarity. otherwise it is getting a little more jumbled up. So, this is A, so this is A1, this is A2, so this side is B, so B1, B2, so this is C, C1, C2. So this is the vector diagram at the delta side, which shows that the delta side phase A voltage, although it does not exist physically, right, because it is basically delta side, we will actually get the line to line voltage, but because it is YgD1, it shows, that means that this phase A voltage at the delta side, even though it is virtual, is actually lagging the phase A voltage at the star side by 30 degree, and then accordingly phase B and phase C. So this completes the phasor diagram at the delta side. Now with this phasor diagram, we have to now reflect these connections at this. So what does it show? It shows that if we connect A2 and B1, so that terminal should be called as phase B. So I connect A2 and B1, and that is called phase B. And it also shows that if I connect B2 and C1 together, that would be called as phase C. So B2 and C1, so it is phase C. And this also shows that if I connect C2 and A1 together, that would be called as phase A. So what I do is I connect C2 and A1 together and I call it phase A. So this is my connection. So obviously, so now this is current is IA. So now my connections of the windings at both the sides, they are complete. So I call it IA, IB, IC, right? And here, so obviously here this current is IA. So let us use some other color. So obviously this current is IA. This current here is IB, and this current here is IC, capital C. And I call that now because of this dot, so then therefore this current here and this current here would be in phase, right? So then therefore I call it, because it is B and A, so I call it IBA. And again, because of these dots are here, so this current would be in phase with this current, and I call it ICB. And because of these dots here, this current would be in phase with this current here, and I call it IAC. So this point is A, this point is C, IAC, this point is B, this point is IBA, ICB, IAC. So this completes the, and the ratio is important. Ratio is, let's say, 1 is to root 3. So ratio, so let's assume that this ratio is 1 is to root 3. So this completes our connection, and this also shows our vector diagram. So you see, just from the knowledge of this, we can very easily make the connection along with the vector diagram. Again, I repeat the process. We first take the primitive network, or rather the primitive transformers connections, or rather primitive transformer windings. Then we first make the connection at the star side, and then we make the vector diagram of the star side, and in that vector diagram we reflect the connections at the star side what we have made, and then subsequently looking at this given value of x, that is basically the vector group, we first draw the vector diagram at the secondary side. Once we draw the vector diagram at the secondary side, then by locating the parallel vectors we do mark the terminals. So once we complete marking the terminals at the vector diagram at the secondary side, then we make the connection at the secondary side reflecting those terminals in the vector diagram. So that's how it actually basically moves. Now with this we have to now write down the equations. So now from this I can write down the equation for IA. IA would be nothing but y is again as usual. So y into VA, that is the voltage. So then therefore here now the voltage is V at the primary side and the reflected voltage. So now this voltage is basically nothing but VAB. So VAB, so it is VA minus VAB. Because of this 1 by root 3, so it would be 1 by root 3, right? So IA is equal to y into VA minus VAB by root 3. So y into VA minus VA by root 3 plus VB by root 3. I capital B would be is equal to y into VB, I mean that is the voltage at the primary side, and the reflected voltage from the secondary side would be BC by root 3. So minus VBC by root 3 is equal to y into VB minus VB by root 3 plus VC by root 3. Please note this is small c, so it denotes the voltage at the secondary side. And I capital C would be given by y into V capital C, and the voltage here is, this point is C and this point is A, so minus VCA by root 3. So it would be equal to y into VC minus VC by root 3 plus VA by root 3. So this completes the equations for the primary side. Now we have to write down the equations of the currents at the secondary side. Now when I look at this, so from this I can say that IA, from this, what is IA? I can write down that IA would be, so at this point if I apply KCL, so at this point IBA is equal to IA plus IAC. So it is at this point IBA is equal to IA plus IAC. So then therefore IA would be IBA minus IAC, right? And similarly IB would be, if I apply KCL at this point, so it would be ICB is equal to IB plus IBA. So it is ICB minus IBA. So it is ICB minus IBA, and I small c would be, again if I apply KCL at this point, it would be IAC is equal to IC plus ICB. So IC would be IAC minus ICB. So it is IAC minus ICB. So these are the relations at the current at the secondary side. So with these relations, now let us write down. So IA is equal to IA is equal to, we said that it is equal to IBA minus IAC. So IBA minus IAC. Now IBA here, now if we look at this connection, IBA is in phase with IA and IAC is in phase with IC, and because of this, I mean, because of this ratio 1 is to root 3, so then therefore I can say that IBA would be IA by root 3 and IAC would be IC by root 3. So it would be IA by root 3, so it would be IA by root 3 minus I capital C by root 3. So I can say that it is 1 by root 3 into I capital A minus I capital C. So what I will do now is 1 by root 3, we will substitute. We have already written down the expressions of I capital A and I capital C in terms of voltages. So it would be, so I take Y common. So Y is common everywhere in the expressions of IA and IC. Y is common everywhere. So I take Y common. So it is Y I take common. So if I now write down the expressions of VIA, it is VA minus V small a. So it is VA minus V small a by root 3 plus V small b by root 3. So that is basically IA, this is IA, and IC is VC minus V small c plus VA, right? So and IC is minus VC minus V small c by root 3 plus VA by root 3, VA by root 3. So that is this. So now we have to do, so then therefore I can say that it is Y, I take Y common, root 3 I will, so VA by root 3 minus V capital C by root 3, and then here minus VA minus V small a by root 3, and here also minus VA small a by root 3. So it is 2 VA by root 3, and so then it would be 2 VA by 3, and then it would be VB by 3 plus VB by 3, and minus minus plus plus VC by 3, right? So this is the equation for IA. So let us give the equation some numbers. So let's say this is equation 1, this is equation 2, this is equation 3, and so this is equation 4, right? So here we have used equation 1 and 3. Now continuing with this, I can say that IB is equal to ICB minus IBA. So it is ICB minus IBA. So ICB minus IBA is now ICB. ICB is IB by root 3 and IBA is IA by root 3. So it is IB by root 3 and minus IA by root 3, that is 1 by root 3 into I capital B minus I capital A. So 1 by root 3 I capital B is VB minus VB plus VC. So VB minus VB by root 3 small c by root 3 minus IA. IA would be from here, so it would be VA minus VA by root 3 plus VB by root 3. Y I take common, so it is minus VA by root 3, so it is VB by root 3 minus V capital A by root 3, and then we get minus minus plus VA by root 3 and by root 3, so it is plus V small a by 3, and then it is minus VB and there is another minus VB, 2 VB, so it is minus 2 VB by 3 and then plus V small c by 3. So I call it equation 5. Okay, so we will continue with this derivation and subsequently with the actual y matrix in the next lecture. Thank you.